Hi everyone, this is the ninth time of integrations of complex variables. Today's topic is isolated singular point and residues. The first is isolated singular point. Till now we have learned the method of evaluation of integral for a given function f. The first, in the Cauchy-Grasset theorem, which was described in section 50, we have the theorem here. If a function f is analytic at all points interior to and on a simple closed contour C, then we have this, the evaluation of integral of the given function f along to the contour C is equal to 0. And also we have the Cauchy integral formula. In section 54 we have the theorem. Let f be analytic everywhere inside and on a simple closed contour C, taken in the positive sense, which means counterclockwise. If G0 is any point interior to C, then we have this. F of G0 is equal to 1 over 2 pi I times integral along to contour C, f of G dg divided by G negative G0. Okay. Here, the assumption is that f is analytic everywhere inside and on a simple closed contour C. But in the integrand here, there is G negative G0 in the denominator. So, with this expression, actually this function is not analytic, but we can evaluate this integral by using Cauchy integral formula theorem like this. However, in this case, the function in itself is not is analytic inside and on a simple closed contour C. So this is the quite nice case. The next is the extension of the Cauchy integral formula, which is described in section 55. The theorem has the same assumption with the original Cauchy integral formula, basic Cauchy integral formula here. So we assume that f is analytic everywhere inside and on a simple closed contour C, taken in the positive sense. So if we look at this formula, f likewise the function f of G is analytic in itself, but with this denominator G negative G0, the f of G divided by G negative G0 to the n plus 1 is not analytic. So compared to the Cauchy-Grasset theorem, the form of the function is modified to the something, yeah, it's not hard to deal with, yeah. However, we can easily evaluate this integral for a given function f of g in the two cases. Next, we are going to consider actually is a difficult case where the function f fails to be analytic here at a finite number of points interior to C. We are going to study how to evaluate the value of integral of the function around that contour C here. Okay, in particular, to deal with this case, we study a specific number called residue and the theory of residues. Each residue contributes to the value of the integral, which means that the integral of the function around the given contour C. Okay, let's go through the details. Okay, to begin with, would you like to define some notions here first? First, we recall in section 24, we have learned this notion, analytic. A function is analytic at a point g0 if it has a derivative at each point in some neighborhood of g0. Okay? So we need to consider neighborhood of given point g0, and then we need to check it has a derivative at each point in the neighborhood, which means epsilon, like a epsilon ball. If we have a point of g0 here, we consider some neighborhood. Normally, we consider epsilon ball, which is a circle with radius r. Then we checked if a function, given function f, has a derivative at each point, in this neighborhood. And we have the notion singularity. A point g0 is called a singular point of a function f if it fails to be analytic at g0, but is analytic at some point in every neighborhood of g0. Okay, so singular point need a function f. I mean, this notion can be properly defined with a function f here. Next is a singular point g0 is said to be isolated. Okay, singular point g0 is said to be isolated if there is deleted epsilon neighborhood, which is given by this. There is a origin and some positive number epsilon, and G naught, the distance between G and G naught is greater than 0 and less than epsilon here. So we can consider this figure. Here we have G naught here. Then the distance of 2 points here, G and G naught, is greater than 0. When the distance is 0, the 2 point is the same. Here. And the distance is less than epsilon. So if we assume this radius is epsilon, then the point G can be placed in this punctured disk here, centered at G naught. Okay, here is the definition of isolated. So we say, when we say isolated, we assume that a singular point G naught, when we study theory of residues in this chapter, we mainly consider this singular point. What I mean is isolated singular point. So we need to remember this notion clearly.